I think you guys had a hypothesis about Max. Sideboard over there. All right, so we were smack dab in the middle of the binomial distribution. And we had a theory about Max and his Crocs. Tell me what it was? They're on the wrong feet. What was the hypothesis about Max's behavior in his Crocs? No, this is perfect. They're on the wrong feet. And did I tell you how many times I watched him? 10 times. Thank you, Johnny. Watched him 10 times. Remember how many times they got on the correct feet? Once. Good. I watched him 10 times. They were on the correct feet 1 out of 10 times. Thank you. Thank you. Perfect. Perfect. Yes, good. What was the hypothesis about Max at that point? Kevin?
Weren't you saying that whichever shoe he grabs first, he puts on a specific foot?
Right, but the shoe that he grabbed was somewhat random.
Okay.
So he would maybe, and I said I'm not sure if that was happening, but even if it was happening, because I know my son pretty well by this point, the shoes are everywhere. Like he doesn't like put them in nice little orderly rows. There's shoes everywhere. So he would essentially randomly grab a shoe and then put it on a right foot, perhaps. But the shoe that's in his hand, half the time is right and half the time is left. Is that fair? I find it terrible, especially being a parent now, that we use the term right to mean two different things. At least two different things, right? It means right, but it also means correct. And it was, I don't know if any parents in the room, but teaching a kid that, the difference of that, it's tricky. It's tricky. Like, sometimes you're like, no, left. I'm like, I'm correct. You know, anyway, sorry. Please, Linda.
I've noticed the same thing with my grandson, and I finally told my daughter to.
This year?
Well, yeah, I went through it 4 kids with him.
Of course.
But he keeps saying, is this my wrong foot? No,
Oh, right, wrong.
Yeah.
That's not why they call it right, is it? Remember the anti-left-hand thing from years and years and years ago?
Yeah.
Has that been centuries old? Is that like a centuries old thing? Like a left person is not right?
Could be.
Demon possessed or something?
It could be a follow-through of that, yeah.
I mean, it's as recent as my wife's left-handed, and they tried to make her not. I mean, she's younger than me, but still about 40. So that's back in the 70s. They gave her one of those spoons that only worked in your right hand, and she figured out how to hold her left hand. It's my wife. She's pretty strong-willed. But I wonder.
I have heard really old stories like they're possessed by demons.
Possessed by demons, right?
Like
Wrong.
Like witches and stuff.
Jay, you got the history? Go.
Yeah, actually. If you ever go to a castle in Europe, you'll notice that all of the stairwells that go up to towers go clockwise.
Go clockwise.
And that was so that invading troops, when they were in the stairwell, they couldn't swing.
Because most of them were right-handed.
Most of them were right-handed.
So they hit the
because
inside.
They thinned out the people who were left-handed by saying it was
Genius.
possessed.
But now I wonder if it even predates that, because here's why. That was based around the idea that most people were right-handed. So then you have to ask yourself, why were most people right-handed? Maybe you don't have to ask yourself this. I have to ask myself this. Why are most people right-handed then? Is it because it's a genetic thing? Like a sword is made, correct? You make a sword to be I'm not a fencist, whatever they call them. But is a sword handed? But we got any fencers in here?
It's gotta be, because it has the thing that goes over your nose.
Right, but you got Inigo Montoya from Princess Bride. I'm not left-handed. Maybe. I don't know. That's all the only fencing I know from that movie. So, supposing they're handed, you have to make them fit a hand. But genetically, like going back, predating castles, predating the English Empire or whatever, what in nature would favor a right hand over a left hand?
Maybe the design of our brain.
Maybe.
I know that certain parts of your left hand that cross over to your right.
Yes.
More.
Only left-handed people are in their right mind. I've seen that T-shirt about that one actually. Yes, but then so then what do I ask them, a bastard? Why? Like, why would that? Right? Why would that favor the right? And they got me thinking. Write this down.
But I bet you if you were to predate that, it would be pretty ambidextrous.
That's what I'm thinking. I'm thinking to go back far enough. There's going to be ambidextrous.
Building things, it would only make sense to go one way or the other. But
So that's what I want to find out.
Stuff, yeah.
That's what I want to find out, Johnny. See, I don't have time for this shit.
So is your son right-handed or left-handed?
He's right-handed, but he's left and right-footed.
So does he normally put the first shoe on his right?
Oh, I don't watch him anymore. They're on the right feet, so I'm like, whatever.
Yeah, but when he was doing that, did you watch him then?
No, I just watched the end result. That's why I can't answer Kevin's question. I don't know what he did. I just watched, because I was trying to be a perfectly objective, non-detectable observer. So, I mean, obviously I'm taking pictures of him, and he sees me taking pictures of him here. But the other times I would just kind of like walk by and look and then go in and write it down and then go back out and play with him. And then never talk about his feet. Unless are your feet cold or your feet hot or something like that. So I don't have an answer. Unfortunately, I wasn't paying that close attention. Great.
Yeah, that's what I've ever had after that.
Say that again? Oh, they've all gone through this.
Yeah.
So, thank you. What's the hypothesis then? Let's come back full circle. And hearing you say that and hearing other parents kind of, whenever I put this slide on the board, every parent in the room chuckles. Because apparently this is pretty common, right?
Yeah.
Mm-hmm. So what's the hypothesis? What do you want to test?
They think they know that way or something.
Boom! Andrea, that's what I'm thinking. Andrea's the other class. Andrea, my God, it's week 8. I should know this by now. He thinks that's right.
He's okay with it.
He's okay with that because in his mind, that's right. Now, the problem is I can't test his mind. I don't know what his mind is thinking. I still don't know what his mind is thinking at age 7. Barely at age 2, but definitely not at age 7. So, what's another explanation for getting his shoes on the correct feet that we can model mathematically? For example, he doesn't understand left and right at all, right? He's 2. He has no idea what left and right are. So, but he knows he has 2 feet and 2 shoes.
Yeah.
So how does he get them on his feet? He puts them on
Randomly.
randomly. We can test that, can't we? If he puts his shoes on randomly, how many times would he get them correct on his feet? If he puts them on 10 times. If he's just guessing, completely guessing.
Do you have to go more than 10?
Well, let's go more than 10, suppose 100. If he guesses when he puts his shoes on, so he grabs, so Kevin, back to your example.
Wait, it's got 50.
50-50! He's got 2 feet, 2 shoes. Now, you have to understand, if he gets the first shoe on the correct foot, he is smart enough to know he's got to put 1 shoe on each foot.
Right.
And he's going to finish the job most of the time. There's been times with 1 shoe. That's okay, too. I do that too myself sometimes, or no shoes. So assuming he gets 1 shoe on the correct foot, the other one is a foregone conclusion. That's a coin flip, if he's just guessing, right? Mm-hmm. Now, I can model that, can't I? I can model that. If I watch him 10 times, does that become binomial?
Yeah.
Of course it does. I got a fixed number of trials, 10. If he's guessing, by default, they're independent. Right? If he's guessing, essentially in his mind, he's flipping a coin. Heads, that one goes on this foot. Heads, that one goes on this foot. Or tails, that one goes on that foot. So it's independent, fixed number of trials, and what's the probability of getting it correct?
Right or wrong?
Right or wrong, 50-50, 1 and 2. So let's model the hypothesis is Max guessing. Is he guessing? This we can model with the binomial. It's got to be binomial. If I watch him exactly 10 times, which I did, I was very careful. I didn't watch him until he got it right. That wouldn't be binomial anymore. I got to watch him a fixed number of times. This is why Gallup calls 1,500 people. They don't say I'm going to keep calling people until the devs have an advantage and then print my report. That's ridiculous. You wouldn't do that. Well, you would, but your job wouldn't last very long. You have a fixed number of trials, so it's definitely binomial. And I'm going to drop a little bit of theory on you today, a very little bit. And the only reason I want to do this is because depending on if you have to take stat classes next, sometimes some profs love the binomial theory. And that's okay. When I say theory, I mean the variables that are often used for the binomial. That's all. That's all. So we've got a fixed number of trials. Is it okay to call it that, fixed number of trials?
Yeah.
Because we're used to hearing that, right? We got a fixed number of trials. That is just called n. For sample size. Boom. You watch it n times. You're used to that label anyway. They're independent. There's no symbol for that, unfortunately. I wish there was. I wish there were. This to me is the hardest thing to prove. If you're going to use the the hardest thing for me is to prove things are independent. If they're not independent, it's pretty easy to see they're not. But it's kind of tricky to prove when something is independent. They've actually made that mistake in court cases sometimes, where they assume something's independent when it's actually not. Anyway, and then the probability of success on 1 trial is just, they usually call that little p. Little p. So just in case you ever run into a prof in a later stat class that likes the theory of the binomial, those are the variables you're going to be using in those. in those theoretical classes. Not in this class. I mean, I don't really care that much for theory. I care more for application. But you might run into one of those, and that's okay. All right. So I watched him for Max. I watched him 10 times, right? How many times should he have gotten his shoes on the correct feet?
5.
I love the word about. Thank you for that. About 5, right?
About 5.
About 5 times. How'd you do that, Tim? How'd you do that?
Well, the average.
Right? How did you put these two numbers together to get 5?
50-50 chance.
Uh-huh. But how'd you get the 10 involved?
Because that was the,
You multiply them!
yeah.
1/2 times 10. That is how you find the average for any binomial experiment. The average, just so you know, and again, for the binomial, if you ever need to find the average number of successes for a binomial, this is the only distribution this works for, which is so freaking cool. The only way, or this is the only one it works for, you just simply take your trials times the probability of success. And that gives you the average. This probably makes intuitive sense to you. If the rate of success of Max's getting his shoes on the correct feet is 50%, that means in half the trials, he's going to get them on the correct feet. Hopefully that makes sense, right? We buy that? Maybe? Maybe.
Yes.
Maybe.
Oh, I'm just trying.
Oh, it's great that I got you. Just grab that guy. Couldn't grab me in the face, sorry. Fair? Good. So, Max got his shoes on the correct feet 1 time.
Yeah.
That's a chuckle from across the room.
He's not an average child.
He's not an average child. Well,
There's outliers.
well. So you're calling him an outlier because 1's not close to 5. What if, let me change Max's behavior because I got me.
Got to stick
Weirded
up with the
out.
little guy.
What if he had gotten them right 4 times and wrong 6 times? Is that weird?
That would be within a deviation.
Deviation. Where'd deviation come from? I love this. So I heard deviation now. I heard deviation, because we have to know what that is, don't we?
Yeah.
You guys are beginning to bridge the gap to 244. I know some of you aren't going to 244. I totally appreciate that. But those of you that are, what we're now discovering is an average is great, but a standard deviation makes an average even better. How close is close enough to 5 to say, we think he's guessing? So 4 and 6, you think he's still guessing?
Yeah.
And Sanders' justification is it's within a deviation. Now, FYI, again, this is purely academic. The way to calculate, you can actually calculate the standard deviation really easily for a binomial too. It's a beautiful formula. I didn't believe it when I first saw it. So here's what it is. You take the square root, watch this, it's gorgeous, of n times p times the complement of p, 1 minus p. That is the standard deviation of a binomial distribution. And I remember 25 years ago or so, sitting where you guys were sitting when my prof, Dr. Taylor, said that. And I raised my hand and I said, because I'm me, what did I say?
Why?
Why? I don't get, wait, why is it that the standard deviation collapses to a formula here, but it doesn't collapse to a formula anywhere else, right? Remember the standard deviation of Bert and Ernie back in the day? We had to calculate the this minus this, and this minus this, and then square them, and then add them, and then divide. He's like, what do you mean, why? I'm like, I mean, why? Like, why is it that that just falls out like that? He's like, I don't understand your question. And that's when I began to realize that many research statisticians don't understand how to teach. They understand how to lecture. Okay. So what I went home and I did was I actually worked through the math myself. And if you want to see it, it's on the enrichment page of your website. It's 6 pages long of algebra to get from the definition that we did with Bert and Ernie to that formula. And I remember sitting at home that night and getting down, this is back when we had kids, plenty of time, and getting done and being like, I'll be damned, look at that, it falls out. I brought it back to class and I showed it to him. He's like, well, of course. Of course? He's like, well, of course, I could have told you that. I'm like, ugh. You could have, but you didn't. And that's when I stopped asking him questions. And whenever I needed anything, I just proved it myself. So that's, your enrichment page actually started with Dr. Taylor that day. Everything on that enrichment page is a direct result of academics not knowing how to explain something to me. And me wanting to understand it more. I don't expect you guys to understand the derivation of that. I don't want you to understand it. Unless you want to understand it. If you want to understand it, it's there waiting for you. And I'll also happily work through it with you if you want sometime. 6 pages of algebra. The important thing, though, is can we model all this stuff in our machinery? Yes, this is why I gave you the programs I gave you to model it in the machine. You don't need to have the clever formulas if you've got something that works for every case. So let's put max up here. Let's see this deviation. Now, of course, we can run the numbers through, right? We know that for max, the average is 5. What's sigma going to be? Well, I mean, you can run the numbers. 10 times a half, which ends up being 2.5 root of 2, like 1.5, something like that. You can run it whatever you need to run it with, but let's not. Let's go to the machine and use this fill and this draw to get the numbers we need. I'd rather not get you guys lost in a sea of formulas. That's not what I want. All right, let's mute max for a sec. Swing over here, fire up your machines.